Hello, this is Mr. Craig, and this is period 3's 20 to make 12 quiz, and I hope you learn from this after you've already attempted to take the quiz, and you're not watching the video before you take the quiz. All right, well, let's get started here. Questions 1 through 3, the set of the letter choices below is a list of terms. Select the one-letter choice that best fits each statement. A choice may be used once, more than once, or not at all. So you have pH, POH, Ka, conjugate acid, conjugate base. Number 1, the acid dissociation constant. Hopefully you know what this is after we've talked about acids and bases. So looks like it's going to be C. All right, measure of the hydroxide or hydroxyl concentration. Since we're looking for hydroxide ions, we can take the negative log of the concentration. Well, that's lovely. And get our POH. So number 2 should be B. Number 3, formed when an acid loses a proton. So something that's formed when an acid loses a proton. So a proton, again, is a hydrogen atom. So if that acid loses a hydrogen to something, then what we have left over is the anion. But also, we can say that that's an acid. Therefore, this is its conjugate base. So whatever conjugate base is for number 3, letter E. Okay. Hopefully those weren't too difficult and quite enjoyable, actually. Those are 3 easy points that everybody should get. So let's look at number 4. Number 4. What is the final potassium concentration in a solution made by mixing 300 milliliters of a 1 molar potassium nitrate and 700 milliliters of a 2 molar potassium phosphate? So what we have here is we're looking for the final concentration of potassium, realizing that potassium nitrate, if we know our volume and our molarity, let's start with that. So we have 300 milliliters, and we know our volume is that, and our molarity is 1 molar. And we know that for every 1 mole of potassium nitrate, we get 1 mole of K. So that right there would give us 0.3 moles. Okay. And then the other one is we have 700 milliliters. And same thing, 1 liter, 1,000 milliliters. We have 2 molar solution of that, and in every every mole of potassium phosphate, we actually get 3 moles of potassium ions. Okay. So here we go. We've got 3 times 2, which is 6, times 0.7 essentially, so oh boy, 4.2. Oh my gosh. So we have 4.2, add that up, 4.5 moles, and our total volume, we have 300 plus 700 milliliters, which equals 1 liter. So we should have E, 4.5 molar solution. Okay, and there I showed all the work. And again, this might be a problem where you may want to circle it and come back to it because it may take you more than a minute or 1.2 minutes to answer this. But you don't need a calculator to answer this question. All right, number 5. Which of the following cannot behave as either a Bronsted-Lowry acid or a Bronsted-Lowry base? In other words, this question's asking which substance is not amphoteric. Amphoteric means it can act like an acid or a base. It doesn't have to be a Bronsted-Lowry acid or Bronsted-Lowry base, but typically it is. So if it is acting like an acid, it has to have a hydrogen to give away. Dead giveaway right there. If it's going to act like a Bronsted-Lowry base, then it has to have a place to put a hydrogen. Well, we have a place to put a hydrogen, so it acts like a base, but this does not act like an acid. So for it to act like an acid, it has to have hydrogens. And I'll give you a heads up too. Oftentimes, amphoteric, not every time, but oftentimes, amphoteric substances have a charge associated with it. And, of course, has at least one hydrogen with that charge. So letter D would be the best choice for number 5. All right, number 6. If 75% of a sample of a radioactive nuclei decays in 24 years, what is the half-life of this radioactive nuclei? So the process or the strategy here is, if it took 24.6 years for 75% of the sample to undergo radioactive decay, we have to find out how many half-lives we have. Well, again, start off with your 100. If you go through one half-life, you're down to half of your original sample. Go through another half-life, you're now down to 25%. Well, if 75% of it decays, we should have 25% remaining. So, if it took 24.6 years to do both of these, we're going to divide this by 2. So, letter D. Okay, so again, there were 2 half-lives. The total time was 24.6 years. Divide that by 2, letter D. Number 7. Okay. What is the voltage in the following half reactions? What is the voltage in the following half reactions when combined in a galvanic cell? Sorry, that's really written poorly. So again, when we're looking at a galvanic cell, first and foremost, we have to have a spontaneous reaction, and if we plan on having a spontaneous reaction, we must have a voltage that is positive. Also, do recall that typically when you're given these equations, they're both reduction equations, so we have to flip one of them to make them an oxidation equation. Well, we already have one that's a positive voltage as a reduction. The other one's a negative value as a reduction. That's the one that we're going to flip, and we're going to make aluminum oxidized, therefore it'll make that a positive value. So that would give us a positive, 1.81. All right, now here's the argument that I often hear from students when they say this. Okay, so you flipped it. So you've got aluminum here, and it goes aluminum plus 3 and 3 electrons. And then we have 10. So we're going to start with 10 metal over here, and get that thing out of the way. We have 10 ions plus 2 electrons. So what we need to do is we need to multiply these both by some value. So this by 2, this by 3. So that cancels the 3 and the 2 electrons out. So we have a total of 6 electrons. How come you didn't multiply the voltages? Don't forget, we never ever multiply the voltages just because we multiply these to get the same number of electrons. Electrons or voltage is an intensive property. As long as we have these things, okay, as long as we have these things, they will produce a voltage. Doesn't matter if you have twice as much, 3 times as much, or 4 times as much, or whatever. As long as we have some of it, it will produce a voltage. Intensive properties. So intensive properties don't care how much you have, just as long as you have it. So again, I always use this analogy in my class that if I had a coffee cup, let me clear this off. If I had a coffee cup amount of water, and if I had a swimming pool amount of water, which of these two substances, or which of these two things has a higher boiling point? Well, if they're both filled with water, they both boil at 100 degrees Celsius. That's an intensive property. However, if I put a flame under each one of these, okay, and I'm incorporating the same amount of heat, I might ask the question, which one would boil first? Well, the one with the smaller volume. That's an extensive property. Intensive properties don't care how much you have, just as long as you have it. Extensive properties do care how much you have. All right, so D should have been our answer. Okay. Number 8 says the reaction where we have calcium reacting with sodium sulfate produces calcium sulfate and sodium. Which of these is the oxidizing agent? Oxidizing agent, first and foremost, we have to recognize that the oxidizing agent has the thing that is reduced. So what we want to find out is who is becoming reduced, or who is getting reduced, or becoming less positive or more negative. So if I look at calcium, it has no charge. If I look at sodium, it has a +1 charge. If I look at calcium, it has a +2 charge. If I look at sodium, it has no charge. So sodium is going from a +1 to no charge. How does it do that? It gains electrons. If it gains electrons, it is being reduced. Therefore, the thing that sodium ions is contained within is the oxidizing agent. Because the sodium is reduced, it allows for the calcium to be oxidized. Remember, oxidizing agents allow for the other thing to undergo that process. So again, the agent always has the opposite name of what it's doing, but it allows the other thing to do that. So the oxidizing agent would be, in this case, the sodium sulfate. Now, a big mistake that a lot of students make is they like to pick things on the product side. Don't do that. That automatically eliminates those two choices. So we only can work with things that are reactants when we're talking about agents. Also, we can only talk about things that are being oxidized and reduced from the reactant side. Never, ever, ever pick anything on the product side to answer who's oxidized, who's reduced, who are the agents. Always look at the reactant side. Also, if this question asked who is the reducing agent, you would by all means say solid calcium. Not calcium with a charge, solid calcium. If I were not given the sulfate, but only say the sodium ions, we would say that the sodium ions are the oxidizing agent, if you weren't given the sulfate. But since you are, you include the whole package. All right, number 9. Which of the following substances is least soluble in water? Solubility rules, guys. Acetate, soluble. That one's out. Nitrates, out. Group 1A, out. Ammonium, out. D. Know your solubility rules. Know what's soluble, and the others will just pop out at you. All right, number 10. Ooh, I really like this question. All right, question number 10, and this is asked quite often on the AP exam. In the reaction where we have nitrogen plus oxygen forms nitrogen dioxide is at equilibrium. Huge. Our system is at equilibrium. Our initial temperature from the first box or first row here, the temperature of the system is 125 degrees. We did an experiment and we found out that at 125 degrees, the percent of NO2 was 35%. When the temperature changed, it went from 125 to 75. There was a change in the amount of product, and this should be predicted. We should be able to know that there will be a change in the amount of the reactants and the products if the temperature changes. The reason why? When the temperature changes, the constant changes. So our K will change. Not our Kelvin, but actually our equilibrium constant. So the products over the reactants. That value changes when the temperature changes. Always. There's no if, ands, or but about this. So when the temperature changes, so does that. So, all right, so the first thing that we need to do is when we look at a question like this is first and foremost determine the shift. So as we go from 125 to 75 degrees, we notice that the temperature goes from the percent goes from 35% to 47%. What does that mean? That means that we are forming more NO2, which means that the reactants are forming more product. Therefore, the shift is to the right. When the temperature is decreased, all right, now you have to ask yourself, okay, we have to treat energy just like a reactant or a product. According to Le Chatelier, if I were to add more nitrogen to a system at equilibrium, what should the reaction do? That's right, it should shift away from the addition. If I add more NO2 to a system that's at equilibrium, it should shift away from the addition. Okay? However, when the temperature changes, the reaction will shift in the direction that will favor the new constant. All right, so we want to treat energy just like a reactant or a product. It can't be both. It can't be exothermic at this temperature and endothermic at this temperature. It's either endo or exo. It's not in between. All right, so based on this information that when we removed energy from the system, there was a shift toward the right, which is just like saying that I'm removing energy or I'm removing a product. So we always shift toward the removal. Since energy is represented on the product side, that represents an exothermic reaction. Now, what's really cool is if you think about this, if I'm cooling the system down, and by nature it's an exothermic reaction, it will try to warm itself back up by producing not only products, but also producing energy. So this system doesn't like the temperature being dropped, so it's shifting toward the right to form more product and increase the energy of the system. Not going to succeed, but it's trying. So since our shift is to the right and energy is exothermic, C is our best choice. Oh, I'm sorry. A is our best choice, sorry. Right and exo. Okay. No Le Chatelier. You will be asked quite a few questions about Le Chatelier on the multiple choice portion. All right. Number 11. Which of the following will occur spontaneously at any temperature? Okay, make sure that you know all four conditions. In other words, the first one, when will it occur at any temperature? That's probably the most important one. So we're looking at delta G equals delta H minus T delta S. Okay. For it to be spontaneous, first and foremost, delta G has to be negative. For it to occur spontaneously at any temperature, we want both of these things to have a negative value. In other words, this part of the equation and the delta H. So the way that we achieve that is by having an exothermic reaction where delta H is negative, and since we are holding a negative sign here, delta S has to be positive, or we're increasing the randomness, the disorder, all those fun terms that everybody hates to use. But under those conditions, delta G will always be negative. So that actually kind of answers this question right off the bat. So we can cancel out the ones that are positive. D. So D's our correct answer for this question. Now, let's go through the other scenarios here. For delta G to be negative, if delta S is negative, we need to have our delta H be negative as well. And the thing that's controlling this to keep delta G negative is our temperature. So if I have a system that's getting organized very well here, because it has a negative delta S, that means it's decreasing the disorder. Again, decreasing the disorder. If it decreases the disorder, it's becoming more ordered. Systems don't like that. The universe doesn't like that. It fights very hard to make sure that you are not staying organized. So we have to make sure that the temperature remains low in this situation for this to be a negative value. Now, how low is low? Well, it depends on what these values are. All right, the last scenario where delta G can be negative is when we have an endothermic reaction, and for it to be delta G to be negative, we have to have one of these as a negative value. So that negative here, we have to make sure delta S is becoming more random. And this, again, based on temperature, so we want to make sure the back half of this equation is pretty important, so we want to have a high temperature. So when both signs are positive, we have high temperatures. When both signs are negative, delta G has to be negative at low temperatures. Now, there is one scenario where it's an endothermic reaction and it's becoming more organized. Regardless of what temperature you put it at, delta G will always be positive. So that is a no-win situation. That is a frowny face for the reactions. All right, number 12. Which of the following reactions would be accompanied by the greatest decrease in entropy? So again, we're looking at the system becoming more ordered. And the first thing that we want to look at is the number of particles. Not necessarily the ratio, but the number of particles. And then once something just happened there. Hold on here, guys, pardon me. I'm going to postpone this for another 4 hours. Okay, so, sorry. So we need the greatest decrease in entropy. So we go from 4 particles to 2 in A, We go from 2 to 1 in B. Here we go from 3 to 2. Well, that one's out. We go from 6 to 7. Not bad. That's an increase. And then 2 to 5. 2 to 5 on there. Huh. 2 to 5 and... Oh, I'm sorry. Yeah, so greatest decrease in entropy. My bad. I'm spacing out here. So, yeah. Actually, C is actually still an option. But the best option is A, because we go from 4 to 2. Wow, that was really not good. Again, read the questions carefully. All right, number 13. When radon 222, I'm sorry, not radon, but radium 226 decays, it emits 2 alpha particles, then a beta, followed by another alpha particle. The resulting nuclei is, so when we do this, make sure that, again, we're keeping track of what these things are. So an alpha particle is a helium atom with no electrons. So we have 2 of those. We have a beta particle that is a 0 and a negative 1, and then followed by another beta particle. So really we have 3 of these things. So when we do our calculation, make sure that all the numbers on the top add up to each other. Actually, let me put that down here. 3 and 0, negative 1. Okay, I'm going to erase that so I can work on it. Okay, so we have our 226, 88 radium, and it emits. So it goes through 3 of those and a electron. Okay, so, and then something's being formed here. All right, so we have 12 on top, so 12 minus 226 is 214. Okay, so we have 2 that have 2 14s. And then 6 on the bottom, so 82. And whoever 80 led. Okay. Oh, whoa. Almost did it too soon there. And then a negative 1, so we have to have an 83 there. Oh, slow down, cowboy. All right, so D is our best choice here. Yeah, and again, slow down just enough to make sure that you're writing these things down. And had I not written down that electron, I guarantee you I would have been most content with writing C down and moving on. So slow down, jot down some things that actually make some sense here. Now, I would not expect you to do these different steps here. Just combine them all together. All right, 14. Looks like we have a reaction here. In liquid ammonia, the reaction represented above occurs. In the reaction, ammonium acts as catalyst, both an acid and a base. No. The conjugate acid of NH3, that one's looking pretty good. The reducing agent, nope. Again, remember what I said about agents. They can't be on the product side, so those guys are out. And so C. Okay. 15, sorbic acid or vitamin C is a diprotic acid with a K1 of 7.9 times 10 to the negative 5 and a K2 of 1.6 times 10 to the negative 12 and a 0.05 molar aqueous solution of ascorbic acid. Which of the following species is present with the lowest concentration? Well, guys, we have a diprotic acid here. What that means is we have a hard enough time removing 1 hydrogen, but we are going to have a really tough time removing 2 hydrogens. So if we start off with this molecule or this acid and we don't have any base or hydroxide that's taking those hydrogens away, this system is not going to dissociate that second hydrogen very well. So yeah, we're going to have a lot of water. We'll have some of that. We'll have quite a bit of that. We'll have some of this. But this, that's going to be real rare to find. So when we look at diprotics or polyprotics, just easier to say, typically we're not going to shed both of those hydrogens. Some might get taken off, but for the most part, no. Only one hydrogen will come off, but not both of them. So E should be the correct answer here. All right, 16. A possible mechanism for the overall reaction is represented above, has the following steps. So here's our rate. Actually, we don't even need that. Here's our slow step, and here's our fast step. Again, when determining the rate law, we include all the reactants up to and including the slow step minus the intermediates. Be sure you know what an intermediate is. An intermediate is something that is produced, I'm highlighting an intermediate right now, something that is produced and later used as a reactant. Again, an intermediate is something that is produced and later used as a reactant. So, when determining the rate law, you'll never see something that looks like that. So B and C are out automatically. So we want to include all the reactants, NO, all the reactants up to and including the slow step. Since NO appears twice, A is our winner. Now, let me give you another scenario here. Let's say that the rate law, we had these guys flipped, and say this was the slow step and this was the fast step. Okay, again, nothing changes. We include all the reactants up to including the slow step minus the intermediate. If the second step were the slow step, we would definitely have two NOs, but we'd also have an oxygen. So if the second step were the slow step, then D would be our rate law. Now again, when writing the rate law or determining the rate law, be sure that you include the word rate, because that represents a rate, K, which is our constant, and then the order of our reactant. Okay? So the best answer for 16 was A. Never ever include products in there. Ever. All right, number 17. Oh yeah, here we go. Which of the following indicators is the best choice for the titration? And then it gives you some ranges of pH. So, all right, before we answer this question, let's ask ourselves, what do these points actually represent? Because you want to know what these points represent. First of all, V, what does V represent? V represents the half equivalence point. What that means is I am halfway to the volume that I need to get my solution to the equivalence point. So it's approximately, what is that, 12 and a half, and I'm trying to get to 25. So V is my half equivalence point. Or at the half equivalence point, the pH at the half equivalence point is equal to the pKa of my acid. Now the pKa is a negative log of my Ka value. So if I know the Ka for my acid and I take the negative log of that, I know exactly where the halfway point is. Okay? All right. Probably the next important value is right here, X. That is the equivalence point. The equivalence point is when we have the moles of the acid, or better, hydrogen, is equal to the moles of the base, or hydroxide. Okay? So moles of acid are equal to moles of base. That is when we are at the equivalence point. And when we do titrations, we always want to make sure that we convert whatever is given into moles so that we can find out when we're at our equivalence point. All right, so I guess now is a good time to answer the question. Since we're at our equivalence point, we want to know when the pH is at about 9. So D would be our best indicator for this reaction. All right, what does Z represent? Z, if I were to flip this equation or flip this reaction and start off with a weak base and titrate it with a strong acid, that would be the half equivalence point for the weak base. All right, now, what does W and W represent? Well, W represents where the system temporarily is acting like a buffer, and it's doing a nice job as we add all this volume of the strong base to the solution. The pH changes from about 3 to 6. That's not too bad. That's not too bad. So this system is trying very, very hard to resist the change in pH. W is where the breaking point. In other words, where it's just too much to handle. So in the next couple of milliliters, the pH is really going to jump from like 6 to 12, almost double. So when we talk about violating, not necessarily violating, but corrupting the buffer system and going to our equivalence point, that's our point there. Now again, if we were going in the opposite direction, Y would represent when we're about ready to destroy that buffer system. All right, so again, what do we say? D for number 17. All right, number 18. Which of the following must be true for a reaction for which the activation energy is the same for the forward and the reverse reactions? Interesting. All right, so the activation energy has to be the same for the forward and reverse. Now again, potential energy. And so if we start off with an amount of energy for our reactants here, and the activation energy has to be the same in the forward and backward, well, that means that our reactants and our products have the same amount of energy. So that means that our delta H must be 0. Now, when we talk about delta H, we're talking about the difference between the reactants and the products. This is the activation energy from here to here. So if we have the activation energy in the forward and reverse direction are the same, then the delta H must be 0. Not too often do you see something like that. Actually, that's quite rare. Number 19. When a solid sample of sodium nitrate is added to a cup of water, the temperature of the resulting solution decreases. Which of the following must be true? All right. Now, we have to ask ourselves a couple things here. First of all, what is sodium nitrate? Well, sodium nitrate is a pretty strong salt. How do we know that? Solubility rules. So when we place sodium nitrate in water, it will break apart into sodium ions and nitrate ions. What is that saying about the entropy of this solution? Is it increasing or decreasing? It's increasing. It's going from 1 to 2. So my delta S is a positive value. Okay, so it's increasing or it's positive. So we know that that's true. We know that that is false. The enthalpy of the solution must be negative. Well, let's see here. So it says the temperature of the resulting solution decreases. So the temperature is going down. Okay. So if this is going down, what that means is as a result of placing that solid in there, the water is losing energy. So if enthalpy is negative, then that would mean that the water is being heated up, or that when you were to touch the outside of it, the container would feel warm. But actually when you touch the container, it actually feels cool because the water's losing energy, so it's going to try to look for something that has energy, which would be you. So that too is not the case. So A should be our correct answer here. All right, number 20. All right. Mixtures that would be considered buffers include which of the following? Now let's make sure that we know what a buffer is. A buffer is a solution that is capable of resisting change to pH. Now, when we add a strong acid or a strong base to a buffer, a good buffer will be able to handle it as long as our concentrations are capable or high enough of handling that strong. So, if we're looking at a buffer system, we can never ever have a strong acid or a strong base as part of our buffer. And think about this. If we have a strong acid or strong base as part of our buffer, then those things are going to dissociate on their own, and they could care less about absorbing any extra hydrogen or hydroxide from anything else. So whenever you make a good buffer, make sure that it's a weak acid or a weak base, weak acid or a weak base, and its conjugate salt. So if you see a strong on a question like this, and I'd be very surprised if you didn't, if you see a strong acid, there's one right there, there's another one. Those two are out. Here, cyanic acid, okay, or actually hydrocyanic acid, and sodium cyanide. That would make a nice buffer. Not that I would recommend it, but it would make a nice buffer. So C should be the correct answer for this. Again, buffers never ever contain strong acids or strong bases. All right, that's the conclusion of this video. Again, I hope this video has helped. One more video to make.